Hello everyone. Welcome to the lecture on quantum mechanics. To begin with, we just look into what all I'll be talking out in this lecture series for quantum mechanics. We start with the failure of classical mechanics, why it was important for quantum mechanics to come into picture, or quantum theory, how it came into picture, followed by Heisenberg's uncertainty principle and an application of it. And then comes the concept of wave function. What are wave functions? What are their use? And how we derive an equation of motion which will give us the expression for wave function, which is the Schrodinger wave equation. Next comes two important applications of Schrodinger equation. First is when we consider a free particle motion. Another is when the particle exists in an infinite potential way. The last and final leg of this lecture will be a few basics of quantum computing, because that's where now the present situation or the present development is heading towards. So the failure of classical mechanics comes at this aspect that classical mechanics was able to explain almost everything for macroscopic objects, but not for matter or which are microscopic. It failed to explain the stability of atoms, spectrum of hydrogen atom, black body spectrum, etc. So for an example, I have given here the black body spectrum. An ideal black body absorbs the entire radiation which falls on it, and when it is heated, it can emit radiation at all frequencies. So the emitted radiation intensity with respect to wavelength is plotted over here. This is an experimental proof where you can see that with respect to temperature, the curve look different. So there is initially an increase in intensity, becomes a maximum at a wavelength, particular value of wavelength, and then the intensity drops down kind of exponentially. Well, you can see that as temperature is increasing, say from here 3000 Kelvin to 4000 Kelvin to 5000 Kelvin, here the wavelength is shifting towards a lower value. So when classical mechanics was applied to explain this concept, so it could explain only this, either only this portion, that is the higher wavelength portion, or it could not explain the lower wavelength or higher frequency, or in a simple word to put it, it is simple sentence to put it, it goes that the entire spectrum could not be explained by classical mechanics. The black body radiation spectrum could not be explained by classical mechanics, because classical mechanics considers that the oscillating charge or the electrons emit radiation or has an energy which is continuous form. So that's where Max Planck comes into picture, and he said that an oscillating atom or charges can absorb or radiate energy only in multiples of a quantity or discrete quantity, which is called as a quantum. So the energy absorbed or radiated will be always a multiple of h into nu, where h is a constant, now called as Planck's constant, and nu is the frequency of vibration. So when this concept was applied, the blackbody radiation spectrum could be explained. Max Planck could obtain an expression which completely describes this blackbody radiation spectrum. The same concept was used by Einstein to explain photoelectric effect. Further, the stability of atom, the spectrum of hydrogen atom, atomic structure in a sense, Bohr's atomic model, which proved that electrons exist in different orbits, and all these orbits have different energy. So each is a discrete energy level. Then we need to understand the concept of matter waves, or which in a sense says that similar to how light has dual nature, matter also has dual nature. So this was put forward by Louis de Broglie. So It's the wave-particle duality and the concept of quantization which resulted into the development of the quantum mechanics. Following with that, we consider that microscopic objects, if we cannot have, and it's not possible to have an exact measurement of position and momentum of a particle at an instant. When macroscopic objects, if you imagine something like a car, a car moving on, you can obviously find its position and momentum at a particular instant of time. But for a microscopic object, it is not possible to have an exact measurement of its position and momentum. So this statement or this principle is known as the Heisenberg's uncertainty principle. If I define delta x as the uncertainty for position and delta p as the uncertainty in momentum, then their product, delta x into delta p, will be greater than or equal to h by 4 pi. In a similar way, the product of uncertainty in energy, delta E, and uncertainty in time, delta T, will be greater than or equal to h by 4 pi. Or delta J into delta theta, another expression that is uncertainty in angular momentum and uncertainty in angle, will be greater than or equal to h by 4 pi. Now, let's try to look into one application of Heisenberg uncertainty principle. We are going to prove that electrons cannot exist inside a nucleus. In order to do that, we assume that they are existing inside the nucleus. So, if they are existing inside the nucleus, then the maximum uncertainty in their position will be the diameter of the nucleus, that is the maximum distance which an electron can occupy if it is existing inside the nucleus. So diameter obviously is given by twice the radius. So 2 into 10 power minus 14 meter will be delta x, that is the uncertainty in position. Taking an approximate expression, of the uncertainty in momentum, we'll get delta p is equal to h by 2 pi delta x. If I substitute all the values for h and delta x and pi, I will get delta p as 5.2 into 10 power minus 21 kilogram meter per second. Next, I'm going to consider that the uncertainty is so less that it is almost equivalent to the momentum itself, momentum of the electron itself. If I know the momentum, let me try to find the expression for the energy of the electron. For that, I need to consider two expressions. One is the de Broglie expression, that is lambda is equal to h by p, wavelength is equal to Planck's constant divided by momentum. And then is the energy of matter wave is coming from Max Planck's expression for a quantum, that is E is equal to h nu or E is equal to hc by lambda. Substituting for lambda from de Broglie expression, I will get E is equal to P into C, that is momentum into velocity of light. So if I do that, I will get, so the momentum we have already estimated, that is 5.2 into 10 power minus 21, multiplied by the velocity of light 3 into 10 power 8, I'll get the energy as 1.56 into 10 power minus 12 joules, or which is equal to 9.75 mega electron volt. So this is the value of energy of the electron if it is existing inside the nucleus. But experimentally, that's from the Rutherford experiment, we know that beta rays which came out of the experiment is nothing but electrons, and the energy of those beta rays is observed to be 4 MeV only. So that means the value of energy of electrons is only 4 MeV. It is not such a high value of, say, something around 9 MeV or 10 MeV. So that means our assumption that electron exists inside the nucleus is totally wrong, and they are not existing inside the nucleus because the energy is actually very less. It's not that high. So we have proved that electrons are not existing inside the nucleus, or they cannot be confined within the nucleus. Proceeding to the next concept, that's called as wave function. So we are now going ahead with this understanding of dual nature of matter, that is particle and wave nature. So I can define a function to that dual nature or the wave function. So a general how we represent a wave like a function of position and time, exactly similar way I can represent it for the particle or the matter. The only aspect being that this function now is a complex function. It's a complex valued function. So if I consider a very small volume or infinitesimal volume dV, which will be a product of dx, dy, dz, that means small elements in all the three directions of x, y, and z, then the probability of finding the particle in the small volume dV will be proportional to modulus of the wave function square multiplied by that volume, that is dx, dy, dz, at a particular time t. And the way I have written, P is proportional to modulus of the wave function square into dV, the volume. The modulus wave function square is called as the probability density, whereas the sign, the function, is called the probability amplitude. It is the probability amplitude. If the probability has to be a real value, or another way to say, or in another way to say that if the matter is existing or the particle is existing, then integral minus infinity to plus infinity psi into psi star, or the modulus of psi square, into dV. That means the entire overall probability of finding the particle in that volume should be equal to 1. If the probability is 1, that means definitely the particle is existing. So we note that modulus psi square I have written as psi into psi star here. I can even write it as integral minus infinity to plus infinity modulus psi square into dV is equal to 1, or in a simpler way, total probability is equal to 1. The psi star is the complex conjugate of psi. A few important properties of the wave function. Here it goes. First one, the wave function should be finite for all values of x, y, z. That means it can never be infinite. The wave function should be single valued, and if there is any boundary existing, then the wave function should be continuous. In the next lecture, we will come across an equation of motion which will give me this expression for the wave function. So see you in the next lecture.